Good afternoon. My name is Irene and welcome to my presentation on signed distance fields. So, what's a signed distance field? A signed distance field is basically a function that takes as an input a point in space, its coordinates, and returns the distance of this point to a given surface, or in the case that we have multiple surfaces, returns the minimum distance to any of them. And here by surface I mean any geometrical object such as a circle, a square, a polygon, a line segment, another point, whatever. Finally, it is called a field since you can apply this function to every point in space. But let us look at an example. For example, let's take the signed distance function of a simple circle, which is simply the distance between our point and the center of the circle minus the radius of the circle. It is called a signed distance field because the points inside our surface will have a negative value, while the points outside the surface will have a positive value. In this example that I have painted over there, I have simply painted the points with a negative value, that is, those that are inside the circle, in orange, while I have painted the points that are outside the circle in cyan, that is, the points that have a positive value. The magnitude of the value, however, corresponds to the distance between the point and the surface. For example, let us look at the gradient of the signed distance field. Here, you can see how I have highlighted the surface in white, and points that are very close to it, both in the positive and the negative side, will have a distance very close to 0, and therefore they are painted in more black colors. Whereas as we get more closer to the center, and therefore we get more negative values, our colors turn more orange. And in the other side, as we get further away from our surface, our points get more positive, and therefore I have painted them in a more cyan color. There are many other shapes, besides a circle, which can be represented using signed distance fields, whose function will appear shortly on screen. Some of these shapes include the square, the triangle, a star, or even a cute heart. As we'll later see, there are ways to combine different primitives, or deform them, or change them in many different ways, and therefore theoretically we could represent every 2D shape possible using signed distance fields. Furthermore, as our objects are defined by functions, mathematical functions, and not by triangles in geometry as we would find in some asset of a 3D object, this means that our objects have infinite resolution, and you can get as close to them as you want without losing any detail. As we'll see later, this has interesting applications, for example in the rendering of fractal shapes. Signed distance fields are theoretically able to be extrapolated to any number of dimensions, as you just need to define a function and define a point in space. However, as it often happens with higher dimensions, it's difficult to represent as we get higher in dimensions. In the case of 2D, it is very easy to represent signed distance fields in 2 dimensions, as you just need to calculate the distance of every pixel in a screen and do as you please with its color, and you can have whatever shape. However, in the case of 3D, it gets more complicated. One way to fix this problem is with the so-called ray matching algorithm. This algorithm could be considered the grandfather of the very popular ray tracing algorithm. For ray matching to work, we need to set a camera in 3D space with all its parameters, such as the field of view or the direction or everything, and we need to set a grid in front of the camera. Each cell of the grid will correspond to a pixel in the image, in the final image, and the theory behind the algorithm is that every cell will represent what the camera sees in that point in space. So therefore we need to launch a ray from the camera through each cell in the grid. In order to see how this algorithm works and functions, we'll look at an example. Here we have sliced our 3D space, so we have a 2D plane, and we can see how we have our origin of our ray, our point of origin, and we have its direction. And we have a collection of different objects, which are all covered by a signed distance field function that returns the minimum distance to all of them. The algorithm proceeds as follows. We take the starting point of our ray, and we calculate its signed distance field function to find the minimum distance to any object. With this distance we can see represented with the red circle. We then advance this point in the direction of its ray, a distance equal to this distance, minimum distance that we found. Why do we do this? This distance is the maximum distance that ensures that we won't cross over any other object, as every object will be in that distance or further away. We then repeat this step with multiple iterations until one of two things happens. The first is that we get a distance smaller than a threshold, in which case we consider that we have hit an object and we can draw the surface in our pixels. And the other case is that we have missed every object and our distance has gotten further away than another threshold, in which case we consider that we have missed any object and we draw the background of the scene. So let's implement this. We'll use a signed distance field function of a sphere, which is the same in 2 dimensions and 3 dimensions and any number of dimensions. And if we implement this, we get the following result. And you will be like, what? Irene, you are tricking us. This is the same as 2 dimensions. You'll see, the problem is that we haven't incorporated any sort of illumination and we simply paint with flat colors. And we can see the 3-dimensionality of our shape. In order to do this, we need to calculate the normal vector of our surface. The normal vector is the vector that is perpendicular to our surface, and we can calculate it with the derivative of our surface. As you probably know by now, the derivative is the same as very small changes, so we can calculate the distance function in very close points to the point that we've hit, and with that we can find our normal vector. And once we have the normal vector, we can implement illumination to a scene, such as Lambert's model of illumination, which incorporates diffuse element and ambiental element, or Funk's illumination model, which also incorporates specular lighting. There are many more other shapes in 3D that we can represent using signed distance field functions, such as a cube, an octahedron, a capsule, or a toroid, more commonly known as a donut. These primitive shapes can be modified to create many other shapes, with things like union, soft union, intersection, or subtraction. We can also do other stuff such as onioning, mirroring, that is symmetry, adding a displacement, or even we can do infinite repetitions. With all these primitives, all these deformations that you can do to primitives, translations, rotations, combination of primitives, we can do more complex shapes. For example, here step by step, you can see how I made a cute little alien. Now, on the screen, you'll be able to see some very complex and very pretty dioramas made with signed distance fields. These are made by Iñigo Quilez, which is a technical artist from the Basque Country, who has worked on several Disney movies such as Brave. And as you can remember, these are not made with triangle meshes as you could find in a video game asset. Instead, these are made purely by mathematical functions. Now, this incorporates some more advanced techniques such as shadows, which you can get by casting a ray from the point that you hit of the surface to the light source, and if you find any other object, it would mean that this point is separated from the light and therefore would be a shadow. It also incorporates ambient occlusion, which is a measure of how a point is affected by nearby objects and nearby light, and you can get that by finding the distance of the very close points to the surface. And it also incorporates something called gamma correction. Gamma correction is elevating the final color to a power, and this makes that the colors seem more realistic because it approximates how humans process color in the brain. And as I've said before, as signed distance fields have infinite resolution and they don't lose detail as you get close, they are especially capable of rendering fractal shapes, as you can see now. If you would like to learn more about this topic, I would recommend, as I said before, Iñigo Quilez. He has a webpage and he has a YouTube page where he explains in a lot of detail how signed distance field works and how to make pretty things with signed distance fields. Another option is messing around on ShaderToy. ShaderToy is a webpage where users upload their shaders and a lot of them are done with signed distance fields, and their code is available and you can see them and understand them. And another option would be Patricio González Vivo, particularly his book called The Book of Shaders, which provides a very basic introduction to shading language. Now this is the end of my presentation, and if you have any questions, me and my alien friend would be glad to answer them.